All right, we can start. So last week there was questions about the idea of scale factors. So we're going to cover a lot of that, and then I had a separate request to go over some trig stuff. So that's what we're going to focus on tonight. So I'll give you a little bit of time for this first problem. So again, these first few are going to have to do with the area, volume, and the idea of scale factors. Okay, so when we take a look at number one, I want to kind of introduce the concept here. So it's going to work anytime we have what are called similar figures, which basically one figure is just like one smaller figure gets multiplied by a number to give us a bigger figure, essentially. And that happens to every one of the single dimensions. So if we look at the parallelogram NOPQ, I'll do something like this. And then that goes to JKLM. And what happens is they're telling us that each side of the smaller parallelogram, or sorry, I should actually go this way. So each side of NOPQ is 4 times JKLM. So I'll do the arrow going this way. So what I use the letter K for the scale factor. That just means the scale factor is 4, which means each side of the smaller parallelogram gets multiplied by 4 to give you the larger parallelogram. And anytime they're talking about area, since it's two-dimensional, is going to get multiplied by k squared, right? So that's kind of the concept tonight is area gets multiplied by the scale factor squared and volume gets multiplied by the scale factor cubed. So we'll get to that in a little bit. So the scale factor squared is 16. All right. So it took a while to explain, but the idea is this: when you approach a problem like this, if each side length is getting multiplied by 4, then the area is just going to get multiplied by 16. So if the area of this one is 8, then to get the area of the bigger one, we're just going to do 8 times 16, which is 128. So the answer is D. So it seems like they don't give us enough information. You could choose your own values and figure it all out that way, but to me, that's longer. It's quicker to just realize, okay, what's the scale factor? And then what are we multiplying by, depending on if it's area or volume.
Okay, that makes sense.
Okay, good. Any other questions for that?
No.
Good. Okay, so try this one now. Okay, so this one very similarly, R has side lengths 208 times the side lengths of S. So that's like saying going from S to R, the scale factor is 208 because each individual side length or each single dimension is getting multiplied by 208. So when we talk about the area going from S to R, then that's just the value the area is getting multiplied by, which should always be the scale factor squared. So in the end, all we have to do is 208 squared, which is 43,264. And that is what C is, because that's what we're multiplying the area of S by to get the area of R. So this is, again, a case of if we can understand these problems through the lens of scale factors, a problem like this is super simple. It's literally just 208 squared is the answer to the problem.
Can you explain like the scale factor more?
Yeah. Yes. So if you think about a single dimension, so that's length, width. Another example would be radius, height, anything that would be measured in, let's say, inches or centimeters or feet. So just a single dimension. when we have similar figures where one is kind of just a bigger version of the other, what we multiply each side length by is called the scale factor. So in this case, since square R has each side length is 208 times square S, then when I go from like the small square to the big square, each side length is being multiplied by 208. That's what the scale factor is. So for instance, if one of the side lengths were, let's say, 4, then I know the other side length would be 4 times 208, which would be 832. So the value that we're multiplying each side length by, that's called the scale factor.
Okay, I get it now.
Okay. And then anytime they're talking about area, what happens with the area is the area ends up getting multiplied by whatever the scale factor is squared. So instead of having to actually choose values here, we could have done it this way: 4 and 4, 832 and 832. This area is 16. This area is 832 times 832, which is a huge number. This is an option to do this problem. So then it's like, well, this area is how many times this area? You would divide them and you would get this. So my point is, if we can just take the time to understand scale factors, you could save a lot of time on these problems. And this is what the SAT does. They create scenarios where you could do it one way and take a while, or you can understand like a quicker way to look at it. Okay, so let's keep kind of going with these. Every one of these that I chose tonight are harder problems. And they're all College Board problems that were considered hard. So, but now we start to get, they can get even more complicated. So take a look at number 3.
What question?
Yeah.
You know the timer that you put up, is it like how much time on the SAT you should around take?
Yeah, good question. So I had been doing a minute 35, which is if you like divide the number of minutes by the number of problems. I just lowered it to a minute 20 just to maybe try to get a couple more problems in when we do the sessions. And also just to kind of see if you can do it a little more quickly. But like a 135 is about what you should expect on each problem, but I just lowered it a little bit just to speed it up just slightly.
I like the scale factor, but I don't understand like what I'm supposed to do with it. Like,
okay. Yep. Good question. That's why I chose 6 of these, because I know it can be a little confusing. So let me try to lay this one out this way. So I'm going to look at, I like to look at the smaller one going to the bigger one, just because we can look at it either way. We can look at what we're dividing by or what we're multiplying by. So I'm going to put NPQR here. I'm going to say the area is 63. And then JKLM, the area is 1,575. And then they give us the longest side of JKLM is 75 feet. So I'm going to write side length is 75 feet. And then this side length is our unknown. So this is what we're trying to find. So here's kind of how it works. Whatever the smaller side length gets multiplied by to give you the bigger side length is what we would call the scale factor. So if I took a rectangle and doubled every side length, the scale factor would be 2. If I tripled it, it would be 3, and so on. So that's what the scale factor is. It's what each individual length gets multiplied by to give us the other similar figure, we would call it.
So to find out this one, would you do the 1,575 divided by 63?
Very good. Yes. So, but we don't have enough information. Yes. This is where it's like the other ones were considered hard. This is like even harder. So we don't have the scale factor because we don't know this length. So then we go to the information we do know. And whatever this divided by this is represents the scale factor squared. because whatever we multiply our smaller area by to get to the bigger area just always represents the scale factor squared. So yes, that's where we would start this problem. Again, I'm setting it all up, but when we're actually doing the problem, that's the first thing we would do. We would do 1575 divided by 63, and we get 25. So what that means is that the smaller area was multiplied by 25 to get the bigger area. But we know now, hopefully, that that is the scale factor squared because I was comparing areas, which means the actual scale factor is 5. And if, again, I have this organized where the bigger one is on the right, to get the answer, I'm just going to divide because the smaller side length got multiplied by 5 to give me the bigger side length, and 75 divided by 5. So what I'm really doing is 75 divided by 5 to give me 15.
I have a question.
Yeah.
So instead of doing that, I actually did like side length over area is equal to side length over area. So I did 75 over 1575 is equal to x over 63. But my answer wasn't right. I got 3 for that.
Exactly. That's because it's not a direct proportion, because the areas don't behave by the scale factor. They behave by the scale factor squared.
Okay. So if I had done 75 over 1575 square is equal to x over 63 squared, would it work?
I think it would have to be. Wait, say that one again.
75 over 1575 square is equal to x over 63 square.
I don't think that would. I think you'd have to square these.
Wait, sorry. Could you set it up then? I'm not too sure.
Yeah, actually, I'm not even sure. I honestly don't know how to set it up that way.
Okay, no worries.
I don't know how to set it up using a scale. Using like a proportion when they're not the same like that. Like when we're comparing areas and side lengths.
Okay. So then instead you would just do is you would divide 575 by 60. Wait, then can you explain what you did one more time?
Yeah.
Thank you.
So what I'm doing is, in general, I'm looking at it like this. The length to go from the smaller one to the bigger one is k, was what I'm multiplying by. Area is always getting multiplied by k squared, and as we'll see shortly, volume would get multiplied by k cubed.
Yeah.
So since the problem gave me the area of both of them, I figured out what k squared was first. So I just say, what does the area of the smaller one get multiplied by to give me the area of the bigger one? And that's 25. So I know that k squared is 25,
But
which
this is a
leads.
rectangle.
Yeah, but it doesn't matter. Every dimension gets multiplied by the same thing. And the
Okay.
fact that they said it was the length of the longest side for each,
Yeah.
that's how we can get away with this.
Okay. So
So,
then,
go ahead.
So then when you divide it by to find the area scale factor, that could work even for the rectangle, even if you're kind of solving it for a square.
Wait, say that last part again.
Because wouldn't k squared be a square, like not a rectangle?
No. Yeah, I'm going to go over this more, but no, if the area gets multiplied by 25, then every individual dimension will end up getting multiplied by 5. I'll show you like a specific example.
Okay, thank you.
Yeah, and then since each dimension gets multiplied by 5, that's where we get the 15 from. So does that make sense where I got the 15?
Since each dimension is by 5. Oh, because Oh, because you just divide the longest side by 5.
Yes.
Okay, that makes sense.
Yeah, so just to show you that it doesn't matter whether it's a square or a rectangle or a circle or any shape, as long as they're similar. If I take an example, if I take a rectangle and I make this 2 by 5, and then I make a bigger rectangle, just to make it easy, I'm going to make the scale factor 2, which means this new length becomes 4 and this new length becomes 10. And if I figure this out the long way, the area of this is 10 and the area of this is 40. And what happens is the area got multiplied
Oh, I get
by
what you
4, which
Okay, so
is
2 squared.
k squared, which is 4. And that'll always work out. It doesn't, if it were a circle and the radius gets multiplied by, say, 3, then the area will get multiplied by 9. There's, if a single dimension gets multiplied by a number,
Right.
again, all of it, this only works if they're similar. If I multiply this length by a number and this length by a different number, then it's no longer similar. It's only working because I'm multiplying every length by the same number.
Wait, okay, yeah, that makes sense.
Okay.
Thank you.
Good. And that's the thing. If we can just understand, like if we can see why it works, then we can start to like use the shortcut. So take a look at this one. Okay. So typically I like to go from like smaller to bigger, but this one, since they gave it to me as a fraction, I'm just going to leave it that way. So basically, just to kind of set this up as a way to look at it, what they're telling me is to go from the actual to the scale. We're multiplying by 1 over 30. I'm just using K. K is what they use in like some textbooks. You could think of it as any letter you want. I'm just staying consistent by like always calling the scale factor K. All right. So notice in this one, they don't even tell us the shape. All they tell us is that the length of each side of the model, we don't even know the shape, is 1/30th the length of the actual one. So that means if we start with the actual, each length gets multiplied by 1/30, which means the area to go from actual to scale would have to get multiplied by whatever k squared is. In this case, that's 1 over 900, which is 1 over 30 squared. So that means the actual area is going to get multiplied by 1 over 900. So now you just take the actual area, multiply by 1 over 900, which is like dividing by 900, and you just get 4. So if on the easy and medium problems, you're relying on using the actual shapes and the actual formulas, which are fine and take a little bit longer, but they still work. In a problem like this, you get stumped because they don't even tell you the shape. So you don't even know what shape to use. So it's about kind of ignoring the shape and focusing more on the dimension, that the scale factor is 1/30th. So the area gets multiplied by 1 over 900. And then you just get the answer kind of quickly.
That makes sense. Thank you.
Good. Okay. Any other questions on that one?
No.
Good. Okay. So now I think eventually, I know I got 2 more of these. Okay. Yeah. This one we incorporate a little bit of percentages, and then I think we finally get to a volume one. But try this one. So basically, we're always in search of our scale factor. This one adds another element to it that's not related to area, and that's the percentages. So I'll talk about that as well. But again, K is just what each length or width or any single dimension is multiplied by. Well, when they say that it's increased by 60%, what we have to realize is that if you increase something by 60%, you start at 100%. You increase it by 60, you're now at 160%. And that in decimal form is 1.6 or 1.60 if you want to see the 60. But so the first thing that has nothing to do with area in this problem is the understanding that something that's increased by 60% gets multiplied by 1.6. So that's the first kind of level to this. Now, if you understand
I have
that,
a question.
yeah, go ahead.
But I thought that with the scale factor that you like square it when it's
We will.
area.
Oh, we will. We just haven't gotten there yet.
But why do you have to change it into the 1.6?
Because that's just like if this were if we think about, I'm going to give an example. So if we have this rectangular sheet, and again, just to make this up, let's say one side length was 8. If I want to find the corresponding side length on that, if I want to increase it by 60%, the quickest way to do that would be to just multiply by 1.6. So 8 times 1.6 ends up being 12.8. So the first part of this has nothing to do with areas. It's just the quickest way to increase something by 60% is to multiply by 1.6. We haven't gotten to the area part yet, but does that make sense? That if you just wanted to increase something by 60%, do you understand why we would multiply by 1.6?
I don't get you got from like the 60% to the 1.6.
Okay. So this is like a separate thing. So when we talk about percent increase, if we do nothing, then we keep 100% of whatever we're talking about. All right. So if we are increasing it by 60%, we now have 160% of what we started with. And then in decimal form, you divide by 100, that's where you get the 1.6 or 1.60.
Oh, okay.
Okay. So all of that is just, again, they're combining things here. They're combining percent increase with area volume. So that part has nothing to do with area volume. It's just we need to know that if something is increased by 60%, the quickest way to do that is multiply by 1.6. So in this problem, that happens to be our scale factor. Well, if I want to know what happened to the area, I want to find my scale factor squared. So I want to do 1.6 squared, which is 2.56. So therefore, that's what my area gets multiplied by. So the final answer is the area that we had times 2.56.
Wait, I have a question.
Yep.
So I mean, I did it like, I guess the backward version of yours. So I don't know if I math this correct, but I did get that number. I did 240 divided by, 240 root 240. And then I multiplied that number by 1.6 and then I squared it. Is that backwards or just yours?
Yeah.
Okay. Is that like the same thing then? I don't
Yeah,
know.
that can work, I think. Yeah.
Okay. Okay. Thank you.
Yeah, that's just assuming it's a square, which it doesn't have to be. But yeah, that works. But in kind of keeping with finding the scale factor, and either way, you have to kind of understand that we're using the number 1.6.
Yes. Okay. All right. Thank you.
Okay. Any other questions about that? Okay. Let's do one more. This is definitely the hardest one. Okay. So I'm going to try to keep track of this. So we got rectangular prism A and rectangular prism B. And we also have, I'm just going to call surface area, and volume. So what they give us is that the area of A is 27. The area of B is 432. The volume of B is 960. And the volume of A is unknown. And from everything that we've been doing so far, the concepts look like this. Whatever the scale factor ends up being, which we don't know yet, the area always gets multiplied by the scale factor squared. and the volume always gets multiplied by the scale factor cubed. Those are just like facts that we have to, again, understand with this. So whatever the area gets multiplied by is considered the scale factor squared, and the volume is scale factor cubed.
So can you like cube the 960 for the like square root?
Not yet, because we don't know the k yet. So we got to use this information first. So the area of the smaller one got multiplied by some value to give us the bigger one. That's what we want to find first. Okay, so that's 432 divided by 27 tells me what we multiplied the area of A by to get to the area of B. And that ends up being 16. And whatever the area gets multiplied by, that is the scale factor squared. So k squared is 16, which tells me the scale factor is 4. But that's not that helpful because they didn't even mention the single dimension. What I need is the scale factor cubed. So I just cube 4 and I get 64. So that tells me that the volume must have been multiplied by 64. So if I work backwards and I do 960 divided by 64, that gives me this volume to be 15. So before we answer the actual question, because that'll be the easy part, do we have questions about all that I just did?
No.
Okay, good. Now just a question, this is typical SAT. They add another layer to make sure that we're paying attention. What's the sum of the volumes? Well, that's simply just 975. All right, so again, if there's easier problems where we can avoid the scale factor, but by doing that, when they give you problems like this, you're not in a good place to try to answer those because like we just don't have enough information to find like all the individual lengths or anything, and we could come up with numbers, but it would just be very, very difficult. So if we can just remember whatever each single dimension gets multiplied by, that's k. The area gets multiplied by k squared, and the volume gets multiplied by k cubed. And then we can just kind of work our way through this to answer a problem like this without really ever knowing any single dimension of these prisms. Or it wouldn't have even mattered that it was a prism. I could change this problem to a cone or a sphere or any three-dimensional figure and ask the exact same question, and you do it the exact same way. All right, any questions?
No.
Okay, and so now we're going to move on to a couple trig problems, but we could definitely touch on scale factors more again on Monday. So let's take a look at number 7. We switch gears a little bit to like right triangle trigonometry. Okay. So the way that I would do these is first, if they give you the value of a trig function, like tan, sine, cosine, tangent of an angle, I would draw just a right triangle. And we PQR, but make sure R is the right angle. So I'll do PQR. And then I'm going to use this information, but I'm going to be very careful. So I'll show you a common mistake and then how I try to avoid that mistake. So hopefully we just refresh. We got SOHCAHTOA. And we're dealing with tangent. So tangent is opposite over adjacent. So if this is P up here, this is the opposite down here, and this is the adjacent here. We want that to be 15 over 8. So I'm going to put that here, but I'm going to circle it. I'm going to explain why. If the tangent is 15 over 8, it doesn't necessarily mean that the opposite is 15 and the adjacent's 8. It just means that's the ratio. So it could be other values that have been reduced. And sure enough, that's what happens here. Because they're telling, so I'm going to switch colors here, that the actual side length of PR is 32. All right, so it's not 8, it's really 32, which means, kind of similar to before, we kind of have a scale factor now. We're multiplying everything by 4. So that means this side is 60. And if we want the perimeter, we need this side. So this is where you can either use Pythagorean theorem, or if you know Pythagorean triples, I'll write down the 4 most common. There's 3, 4, 5, 5, 12, 13. Then there's the 2 a little kind of lesser known, which is this one, 8, 15, 17. And then I would say 7, 24, 25. So 8, 15, 17 means this one is 17. But again, it has then been multiplied by 4. So that's 68. And then finally, the perimeter is just 32 plus 60 plus 68. So the final thing, again, they keep stacking like tasks for us to do. The final thing is the overall perimeter is 160. Questions on that?
No, that makes sense. Thank you.
Nice. Now, with the fact that this version of the SAT, it's all calculator, it's up to you how much you want to spend making sure you know the triples. They definitely can save time, but knowing you have a calculator and Desmos, it's the Pythagorean theorem is not too difficult in any situation because you can always use a calculator. But I definitely think it's helpful to know these, and then you can not have to type anything in at all.
Quick question. You said that you're writing down the most common ones, so that means are there more, or just those that you should really know?
Yeah, okay. So a Pythagorean triple is just any 3 numbers that satisfy the Pythagorean theorem that are whole numbers. So there's theoretically there's an infinite number.
Oh, I see. Okay.
Yeah. And then as far as ones that you typically see either on SATs or ACTs or just in school in general, I think these are the most common, but there are other ones that show up as well. Like 9, 40, 41, I think is one. But these are the first 2 is kind of is it. Yeah, they're not going to get an argument from anybody there. Those are the most popular. These 2 I tend to see more. There's a couple other small ones.
Okay.
But yeah, you could kind of keep going with them. At some point, it's not worth. I would say this is like most important. This is, if you have these 2, you probably won't come across any others.
Okay.
On the SAT.
So.
Okay. Exactly. And you always have a calculator. So it's not as big of a deal as it used to be, because there used to be a non-calculator section and they would ask these a lot. So it was really important to know a lot of them. It's not as important now, but I still think it can save you a little bit of time by knowing them.
Okay. Thank you.
Yep. Okay. So let's keep going. Couple more trig problems. So try this one. Okay. So here is one where we can save a considerable amount of time if we do a couple things. So anytime I make these suggestions on the SAT, there's always an exception, but for the most part, they'll work. If they're giving you a trig problem related to similar triangles, you really only need to focus on one of those triangles, because trig ratios, they're ratios that reduce. So to write out both of them and go through it kind of wastes a lot of time. So I'm going to show you what I mean by that. I am only going to draw out the QRS triangle because they ask me the value of tan Q. So when you're drawing these out, just make sure you follow what they say is the right angle. So they say S is the right angle. So I'm just going to put Q down here and R here. Okay. Now, the question is, well, they gave me the cosine of L, but there's no L here. So all we do is we realize that these are given in, they even tell us L corresponds to Q, but even if they didn't, L is the first letter and Q is the first letter. So cosine L is cosine Q because they're the same angle. So I just ignore the L and I just think of that as Q. So cosine is SOHCAHTOA, adjacent over hypotenuse. So adjacent is 24, hypotenuse is 25. And this is extremely important. In the last problem, I made sure to like circle those and make sure that I saw them as ratios and not definitive side lengths. In this problem, though, they're asking me the tan of Q. So it doesn't, I'm going to end up dividing anyway. So what I could do is just go back up here, right? I just listed this one, 7, 24, 25. So this side has to be 7. So the tan of Q is opposite over adjacent. So the answer to the problem is 7 over 24. So this LM is 4 times the length of QR. It never factors into it. We don't have to worry about that because we were asked the trig function, which is, again, if we had figured it out, we might have had larger numbers, but they would all reduce to 7 over 24.
That makes sense.
Good. Because, or else we would have gotten these values for this triangle and then multiplied or divided by 4. It would have been a lot longer. So just when you're asked the trig function of similar triangles, just focus on the triangle that is the one they ask about. So I think if we look, we have another example. Okay. So again, this part of it is kind of trying to get you to do more work than you need. So what I would do is go right to what are we looking for? The tan of K. So I really only want to draw that triangle. So I just, again, got to make sure that I make L the right angle. So I don't know, do JKL. And then the given information is I just want to see that G goes with J, or they actually tell us. They don't have to tell us that. We could know just because they're both first letter. So this is like the tan of J, and tangent is opposite over adjacent. And then they just want the tan of K. Well, I don't even have to find the hypotenuse here because the tan of K is opposite over adjacent, but the opposite is now 21 and the adjacent is now 20. So that's it. And if for some reason, I can't think of it off the top of my head now, but if for some reason you draw the one triangle and it's necessary to draw the other one, then you might have to do that. But if you go into it thinking I'm only going to draw the one triangle, almost all the time you're going to save time. But there's a problem that could come up, I guess, where you might need that other triangle, but for the most part you won't. And they're looking for you to kind of do that, to draw out both and do it that way. But if you really understand how trig ratios work, then you can do this shortcut of just focusing on the one triangle. Okay, any questions? Okay, then we are going to do one more. Okay, this one's a little different. This one's more of a conceptual one that we just have to understand what they're really telling us here. And to kind of understand that, I'm going to use a right triangle to explain it. So let's say we have A is here and B is here, and we'll just call that C. So if I think about what the sine of A is, that's going to be the opposite, which I'm going to call BC, over the hypotenuse, which I'll call BA. Okay, so opposite over hypotenuse. And then if I look at the cosine of B, so what I'm doing is I'm switching to this angle. And cosine is adjacent over hypotenuse. But now from B's perspective, the adjacent is BC, and the hypotenuse is still BA. So what that means is the only way the sine of A is going to equal the cosine of B is if they are two angles within a right triangle. And what that really means is if they add up to 90, because all the angles of a triangle add up to 180. And if it's a right triangle, 90 of those is being used up here. So these two angles in a right triangle will always add up to 90. So when you see something like this, where the sine of A equals the cosine of B, it just means A and B, I should do this correctly, angle A and angle B are what's called complementary, which is they add up to 90. So once you get that concept, it's a really simple algebra problem. It's just this angle plus this angle has to equal 90. Right, and then it's just 4n plus 10 equals 90. Go up here, 4n is 80. Oops. And then n is 20. Right, so the key is just realizing that what they really are telling you is that A and B add up to 90. Okay, questions?
Thank you.
Okay, cool. All right, then we will stop there. Yeah, thanks for coming at this different time. Next week, we'll be back at Monday at 6 o'clock, our normal time. I'll send an email about all that, and I'll just see you on Monday.
All right. Thank you. Bye-bye.
Okay, bye.